Now let's go to the section 11.2. Okay, we talked about Green's function of this video. Well, the Green's function can be considered look like this. Okay, actually you can consider this one as a work done. The vector field is PQ, and then dr just go dx dy. Okay, they take the dot product over here. Okay, so Green's theorem tell us that it tells us that so long as C, this path, okay, is a positive oriented. For example, we just consider the anti-clockwise is the positive orientations, okay, and D is the region bounded by this curve, okay, look like this form. Okay, so, and also C is piecewise smooth, and also it is closed curve. It must be closed, okay. So the line integral, well, over here it means it is closed, okay. So this line integral, of course, we can consider this one as a work done, okay. Can be considered as what? It can be right in this form. That means the function in front of dy, this q, and then take a x derivative over here, okay, and then minus p, take a y derivative. You notice that this one, if it is one a consecutive field, this one equal to 0. However, if this one is not a consecutive field, this one may be equal to some functions. It may not be equal to 0. Okay, so you can find out you just use a double integral to compute this one. You remember that for double integral, it may be a type 1 or type 2. It's very easy to compute it. Okay, but there's another problem. The problem is that, okay, if the region D, okay, over the region D, there's some points, for example, P1, P2, P3, P and Q, these two functions. It may not have a continuous derivative over these 3 points. Of course, you can consider there's an n points, it doesn't matter. So by that time, we would like to, if we want to compute this, if we want to use a Green's theorem, it's better for us to construct 3 more paths. This path, this path, this path. Okay? But the outside path is this one. Okay? But the inside path, you can consider the outside path is a anti-clockwise in direction. However, the inside path, these 3 paths are clockwise in direction, just opposite in direction. But you can see that the region D is always in the left-hand side of the outer path and also in the left-hand side of the inner path. Can you see it? If it is clockwise direction, the left-hand side is this region. Okay, the left-hand side is this region. Okay, so you may consider just remember the region when it changes into the just by Green's theorem. Okay, the region must be in the left-hand side of the path. Okay, but why is it so? Well, actually, let's look at this graph. Indeed, you may consider this one as this one. Okay, so if you want to run over from the outer to the inner, okay, for example, we just start from this point and then we passing through to over here, and then we take a line integral over here and then passing through over here, passing through over here, passing through over here, and then go back here. Afterwards, we just go back because this path and this path over the same region, okay, same. This is because they are opposite in direction, the results will cancel each other. Okay, so it runs over here, so it passes through the lower part. Over here, pass through lower part. Over here, pass through the lower part. Over here, pass through the lower part. Okay, so it's better for us to divide this whole region into two parts, D1 and D2. So we just put that D1 is over here, D2 is over here. So for the first region, it looks like this. Okay, just equal to this. Okay, the second region is over here. That's the reason why for the outer it preserves the anticlockwise. However, for the inside, these two are cancel each other. These two cancel each other. These two cancel each other. These two cancel each other. So we have the inner path, inner closed curve. This one is a clockwise in direction. This is clockwise in direction. This is clockwise in direction. That's the reason when PQ do not have the continuous positive direction on some points P1, P2, P3, P4, P4, and P5 and go on. Okay, for example, for simplicity is P1, P2, P3. Then we can draw any curve over here, any curve over here, any curve over here, and then through the new path, okay, this region D1 and this region D2, PQ are continuous. Then you can apply the Green's theorem. So when you want to compute this region, okay, then therefore you should use the Green's theorem, and then you need to minus the result of integral over this path, and over this path. Is that clear? Now let's use an example 6 of our tutorial 11 to demonstrate why should we learn the Green's theorem. For some line integrals look like this. Okay, it's hard for you to compute it, even though it is the curve C is very common. For example, this is a circle. We just want to compute the line integral over this path. It is x squared plus y squared equals to 3 squared. Okay, over here. But you can see that over this one, if you directly compute this, you can consider x equal to cosine 3 cosine t, y to 3 sine t, then dx, dy look like this, then t of course from 0 to 2 pi, and I just can be written down in this form. It's impossible for you to compute this. You can see that. However, when we change this question into we use Green's theorem to change this question. So therefore, we just consider P is equal to this, P is equal to this, Q equal to this. But very easy, you can see that when Qx, this term equal to 0, when Py, this term equal to 0. So you can very easy to compute that Py just equal to 3, Qx just equal to 7. So Qx minus Py just equal to 7 minus 3 equal to 4. So this one by Green's theorem, it just equals to what? The Qx minus Py over the region D. The region D is over here. Okay, this is region D. It is the circle. Okay, but this one just go to constant. So it's just go to 4 times the area of this region. The area of this region just equal to area of the circle. It's just equal to 4 times pi r squared. So it's just equal to 36 pi. If you just want to directly compute this, okay, I think it's impossible for you to compute this integral. It's hard, at least it's very hard to compute it. But if you use Green's theorem, this one is very easy stuff. So you can see the power of the Green's theorem. We also have a 3 direct results from Green's theorem. Okay. Well, the direct result is this. Suppose this curve is closed curve. Okay, it bounded a region D over here. Okay. Well, you know that because the Green's theorem, okay, this integral, it just equals to what? The area D. Well, you can consider this is the P equal to 0, Q equal to X. So Qx just equals to 1. And then Py equal to 0. This is 1 and then dA. So that's the reason it is the area of this region D. Well, in the same manner, okay, this is minus y dx. That means P equals to minus y and Q equal to 0. So Qx 0 and then the Py it just equals to minus 1. Okay, this is minus 1, it just equals to 1. So that's the reason. This one is also equals to the area of the region D. So these two add together just equal to 2 times the area of D. And then divided by 2. Therefore, this is just the same as the area of the region D. Well, we will use this formula to find out the area of the ellipse. Now let's look at this example. In the tutorial 11, example 7, we want to find out the area of the ellipse, okay, of this form. So you can see that the ellipse look like this. The semi-major axis equal to A, semi-minor axis equals to B, okay, because under X is A over here, under Y is B is over here. So we want to find out this area, okay. Well, as we know that the direct results from Green's theorem, this area can be considered as 1/2 of the closed curve. Okay, this is closed curve is C over here. Okay. So first of all, we would like to parameterize our curve. Okay, because of this one, we consider x equal to A cosine t, and then y equal to B sine t. So we have this. Of course, when it circle around, that means t equals to from 0 to 2 pi. Therefore, dx over here just equal to minus A sine t, dy just equal to B cosine t dt. Well, when we plug in all these informations into the formula, because the area A just equal to this formula, just equal to this, okay? So x equals to A cosine t, dy over here is B cosine t dt, and then minus y is B sine t, okay? And then dx just equal to this, okay? When we plug in all these informations, we know that we have a common factor AB. We take it outside, it becomes cosine square plus sine square. This one equal to 1. So it is AB dt. So therefore it is AB divided by 2 and then t. Okay, evaluated from 0 to 2 pi. 0 to 2 pi, plug in. Therefore it's just equal to pi AB. So if you know the Green's theorem, this integral is very, very easy. The area of this ellipse is very easy to find out. If you don't know the Green's theorem, this one is well, a little bit tedious. The computation for this area is a little bit tedious. Okay, so you know that the Green's theorem has another very, very useful for the rather useful usage over here. Let's do one more example and then we'll close our video. Now let's look at the question in T11, Q19. we want to evaluate this integral, this line integral. Okay, C, okay, this path is the ellipse over here. So we would like to consider this way. Okay, then we just derive the 2 to both sides. We get x squared over 2 and plus y squared over 1 equals to 1. So therefore, we just change the 2 to square root 2 all square. So we get this. This is the length of the semi-major axis. So this is square root 2. This is 1. So we get this circle, this ellipse. Okay. Well, with the help of this one, we know that means this one equals to P, this one equals to Q. So we want to find out what is Py. It just equals to 4y to the power 3. Qx just equals to 2 to the power 2y to the power 3. So imply Qx minus Py, it just equals to minus 2y to the power 3. So the integral, we would like to use Green's theorem. This integral becomes I just equals to the double integral over the region D, and then Qx minus Py, and then dA. So we will consider this one look like a type 1 integral. Okay, this is square root 2. This is square root 2 minus square root 2 over here. So we would like to divide this one because this result. So we have this one becomes so minus square root 2 to square root 2. This one is just equals to, well, y1, y2. This is y1 equals to minus 1/2 square root 2 minus x squared. This is 1/2 square root 2 minus x squared. Okay, so this is minus square root 2 minus x squared over 2. This is square root 2 minus x squared over 2. Okay, so this one is equal to minus 2y cubed, and then dy, and then dx. But look at this. This one, it looks like minus a, okay, and also for x, it is also symmetric. For this case, okay, we know that this one just equal to 0 by symmetry, because this one is an odd function. So if you don't believe this, you can just do it by yourself. Okay, just by direct computation, because this one is just use this one, take it outside, minus 2 take it outside, and then this is y to the power 4, and then you substitute these 2, and then you can see that the whole result just equal to 0. So for this question, it's better for you to use the Green's theorem rather than just directly compute the line integral. That's all.